Let me ask you to do something right now. It's simple. Look at a clock. Any clock. The one on your wall, the one on your phone, the small one ticking in the corner of your screen. Watch the second hand move or watch the digits change. 1 second, 2 seconds, 3 seconds, each interval identical. Each tick perfectly metered, perfectly predictable, perfectly predictable, perfectly ordinary. Now let me ask you something far less simple. What exactly is happening between those ticks? What is a second? You might say it's a unit of time, and you'd be right in the way that saying water is wet is right, technically true, but it doesn't tell you anything about the ocean, because that tick you just watched, that serene and dependable little tick, is concealing one of the most disturbing truths in all of science. That tick is a liar. Not because it's inaccurate, but because it's making you believe something about reality that isn't true. It's making you believe that time is simple, that it flows like a river, at one speed, in one direction, the same for everyone, everywhere. That 1 second for you is the same as 1 second for me, the same as 1 second for an astronaut in orbit, the same as 1 second for a particle screaming through the upper atmosphere at nearly the speed of light. It isn't. And it took one person, one patent clerk in Bern, Switzerland, with an unruly head of hair and a mind that could see around corners in the fabric of the universe, to show us why. His name, of course, was Albert Einstein. And in 1905, at the age of 26, he published a paper that would quietly detonate beneath the foundations of physics. It was titled On the Electrodynamics of Moving Bodies, which is perhaps the most boring title ever given to a document that would fundamentally restructure humanity's understanding of space, time, motion, and reality itself. The paper introduced what we now call the special theory of relativity, and special it was, not in the casual sense, but in the precise sense. It dealt with a special case, objects moving at constant velocities relative to each other, no acceleration, no gravity, just pure, smooth, uninterrupted motion. And yet from that seemingly simple restriction, Einstein extracted conclusions so radical, so counterintuitive, so deeply unsettling, that even physicists at the time struggled to accept them. But accept them we did, because the universe, it turns out, does not care about our intuitions. It cares about consistency, and Einstein's theory is, above all, a theory about what must be true if the universe is to remain consistent. To understand how we got there, you need to understand two ideas, just two. They are called postulates, which is a fancy word for starting assumptions, things Einstein took to be true and then followed wherever they led, no matter how strange the destination. The first postulate is this: the laws of physics are the same for all observers moving at constant velocity relative to each other. This is not new. Galileo essentially said the same thing centuries earlier. If you're on a perfectly smooth train moving at a constant speed, and you close the blinds so you can't see the landscape passing by, there is no experiment you can perform inside that train that will tell you whether you're moving or standing still. You can toss a ball in the air. It comes straight back down, just as it would if you were standing on solid ground. You can pour a glass of water. It behaves normally. The physics inside the train is identical to the physics outside it. Motion, in and of itself, is undetectable from within. It is, as physicists say, relative. There is no absolute moving and no absolute still. There is only moving relative to something else. This first postulate is intuitive, sensible, almost obvious. It is the second postulate that breaks everything. The second postulate says this: the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Read that again. Let it settle. Because it sounds simple, and it is simple to say, but it is extraordinarily difficult to truly absorb. Consider what it means. If you're standing still and I shine a flashlight past you, you measure the speed of that light at roughly 300 million meters per second. Fine. Now imagine you're in a spaceship, racing toward me at half the speed of light, and I shine the same flashlight in your direction. Common sense, the everyday intuition you've built from a lifetime of throwing balls and driving cars, tells you that you should measure the light approaching you at 1.5 times the speed of light. Your speed plus the light's speed. That's how velocities add. That is how they have always added for every object you have ever encountered. But light doesn't care about your common sense. You would still measure the speed of that light at exactly 300 million meters per second, not 1 meter per second more. And if you turned your ship around and fled from the light at half the speed of light, you would still measure it approaching you at 300 million meters per second, not 1 meter per second less. The speed of light is not just fast, it is fixed. It is the same in every direction for every observer at every velocity. It is the one absolute in a universe that is otherwise saturated in relativity. Now, this was not just a philosophical musing on Einstein's part. This bizarre constancy of light had experimental support, and the story of that experiment is one of the great dramas of 19th century physics. In the late 1800s, physicists believed that light, like sound, must travel through some kind of medium. Sound needs air, ocean waves need water. So light, they reasoned, must need something too, and they called this hypothetical something the luminiferous ether, a substance that supposedly permeated all of space, invisible and intangible, but present everywhere as the fabric through which light waves rippled. If the ether existed, then the Earth, hurtling through space in its orbit around the sun, must be moving through it. And if the Earth is moving through the ether, then the speed of light measured in the direction of Earth's motion should be slightly different from the speed of light measured perpendicular to it, just as a swimmer moving with a river current covers ground faster than one swimming across it. In 1887, two American physicists, Albert Michelson and Edward Morley, devised an extraordinarily precise experiment to detect this difference. Their apparatus, called an interferometer, split a beam of light into two perpendicular paths, bounced each beam off a mirror, and then recombined them. If the Earth were indeed sailing through an aether wind, the two beams would travel at slightly different effective speeds, arrive back at slightly different times, and create a telltale interference pattern, a kind of fingerprint of the aether's existence. They found nothing, no difference, no aether wind, no variation in the speed of light in any direction, at any time of year, regardless of how the Earth was moving. The experiment was repeated with increasing precision by other physicists, and the result was always the same. Light, it seemed, traveled at the same speed no matter what. The ether did not exist. The medium through which light supposedly traveled was a ghost, a fiction, a beautiful hypothesis slain by an ugly fact. This was a crisis. Without the ether, the behavior of light made no sense under the existing framework of physics. Physicists scrambled for explanations. Some proposed that objects physically contracted in the direction of their motion, that the apparatus itself was being squeezed by its passage through space, masking the expected result. This idea, advanced independently by George Fitzgerald and Hendrik Lorentz, was mathematically productive, but physically unsatisfying. It was a patch, not a principle. Einstein saw it differently. Rather than trying to explain away the constancy of the speed of light, he embraced it. He took it as a fundamental truth about the universe, and asked a question that no one else had thought to ask. If the speed of light truly is the same for all observers, what must be true about space and time to make that possible? The answer, as it turns out, is that space and time must be flexible. They must bend, they must yield. They must conspire in perfect mathematical harmony to ensure that every observer, no matter how fast they are moving, always measures the same speed of light. And the way they conspire is through time dilation and length contraction, phenomena so alien to everyday experience that they sound more like science fiction than science. But they are real, measured, confirmed, undeniable. Let's begin with time dilation, because it is perhaps the most viscerally shocking consequence of Einstein's second postulate. And the best way to understand it is through a thought experiment, a beautifully simple one involving a device called the light clock. Imagine a clock that works like this. A single photon of light bounces vertically between two perfectly parallel mirrors, one at the top and one at the bottom. Each time the photon completes one round trip, up and down, the clock registers one tick. It is the simplest clock imaginable. No gears, no springs, no electronics. Just light, bouncing. And because light travels at a known constant speed, we can calculate exactly how long each tick takes. If the mirrors are, say, 1 meter apart, the photon must travel 2 meters per round trip, and at 300 million meters per second, each tick takes an extraordinarily tiny but perfectly defined interval. Now, Place this clock on a spaceship and let that spaceship fly past you at a tremendous speed, say 80% of the speed of light. You, the outside observer, are standing on a platform watching the ship streak by. The passengers on the ship go about their business. They look at their light clock. It ticks. The photon bounces straight up and down between the mirrors, just as it always has. Nothing unusual. One tick, another tick. Time passes normally for them, but what do you see? You see something profoundly different. From your perspective, the spaceship is moving. And because the spaceship is moving, the bottom mirror has shifted to the right by the time the photon reaches the top mirror, and the top mirror has shifted further to the right by the time the photon bounces back down. So from your vantage point, the photon is not traveling straight up and down. It's traveling in a zigzag, a diagonal path, like the letter V, then another V, then another. And here's the key. A diagonal path is longer than a vertical path. The photon, from your perspective, has to cover more distance per tick than it does from the passenger's perspective. Now, and this is where Einstein's second postulate delivers its blow, the speed of light is the same for you as it is for the passengers. You cannot say the photon is moving faster to compensate for the longer path. It isn't. Light always moves at the same speed. So if the photon is covering a greater distance at the same speed, then each tick of that clock must take more time. The moving clock, as seen by you, ticks slower. This is not an illusion. This is not a trick of perception. The clock on the spaceship is genuinely, physically, measurably ticking at a slower rate than your clock. And it's not just the light clock. It's every clock. It's every process. Chemical reactions on that ship are slower. Biological processes are slower. The aging of the passengers is slower. Time itself, for everything on that spaceship, is passing more slowly than it is for you. The passengers don't notice, because everything around them, their heartbeats, their thoughts, their wristwatches, is slowed by the same factor. To them, life feels perfectly normal. But relative to you, they are moving through time at a reduced rate. The mathematics behind this are captured in a quantity called the Lorentz factor, usually denoted by the Greek letter gamma. At low speeds, everyday speeds, the kind of speeds at which you drive your car or throw a baseball, gamma is so close to 1 that the difference is immeasurably small. At 10% the speed of light, time dilation amounts to roughly 0.5%, barely a whisper. But as velocity climbs toward the speed of light, gamma grows without bound. At 90% the speed of light, a moving clock ticks at less than half the rate of a stationary one. At 99%, it ticks at about 1/7 the rate. At 99.99%, it ticks at about 1/70 the rate. And at the speed of light itself, gamma reaches infinity, which means time stops entirely. A photon of light, if it could carry a clock, and in a sense it is a clock, would experience no time at all. For light, the moment of emission and the moment of absorption, even if they are separated by billions of years and billions of light years from our perspective, are the same moment. Light does not experience duration. It exists from its own frame in an eternal, singular now. And this is where the thought experiment transcends physics and starts touching something almost philosophical, because it raises a question that reaches far deeper than clocks and spaceships. If your clock ticks at one rate and my clock ticks at a different rate, and we are both right, then whose time is real? The answer that Einstein forces upon us, is both, and neither. There is no universal clock. There is no cosmic timekeeper ticking away some master time that everyone shares. Time is local. Time is personal. Time is a function of how you move through space. This realization, disturbing as it already is, leads directly to another consequence that is, if anything, even more unsettling. It's called the relativity of simultaneity, and it strikes at the very heart of what we mean when we say now. Consider two events. A lightning bolt strikes the front of a moving train, and at the same instant, a lightning bolt strikes the back of the same train. An observer standing on the platform, equidistant from both strikes, sees the light from both flashes arrive at the same moment and concludes, quite reasonably, that the two strikes were simultaneous. They happened at the same time. But now consider a passenger sitting in the exact middle of the train. The train is moving forward. The light from the front strike is approaching her, and the light from the rear strike is receding from her. Or rather, she is receding from it. Because the speed of light is the same in all directions and does not depend on the motion of the train, the light from the front strike reaches her first. She concludes, equally reasonably, that the front strike happened before the rear strike. The events were not simultaneous. Who is right? Both of them. And this is not a matter of opinion or perspective in the casual, everyday sense. This is a structural feature of the universe. Simultaneity is not absolute. Two events that are simultaneous in one frame of reference are not simultaneous in another. And if simultaneity is relative, then so is the ordering of events in certain cases. Things that happen at the same time for you might happen in a different sequence for me. Your now is not my now, and neither of us is wrong. Think about what that means for the concepts of past, present, and future. In our everyday experience, the present is a knife's edge, a universal dividing line between what has happened and what hasn't happened yet. We imagine that everyone, everywhere, shares the same present, that there is a cosmic now stretching across the universe, and everything on one side of it is the past, and everything on the other side is the future. Relativity demolishes this idea. The present is not a universal concept. It is observer-dependent. What is in your present might be in my past or my future, depending on how we are moving relative to each other. The neat division of time into a shared past, a shared present, and a shared future is an illusion, a very convincing illusion, because at the speeds we normally move, the disagreements are incomprehensibly tiny. But at relativistic speeds, they become dramatic. They become undeniable. And here's what makes this not just a theoretical curiosity but a physical fact. We have tested it. We have measured it. Relativity is not a hypothesis. It is among the most thoroughly confirmed theories in the history of science. Consider, for example, the satellites of the global positioning system orbiting above your head right now. There are roughly 24 of them, circling the Earth at an altitude of about 20,000 kilometers, traveling at approximately 14,000 kilometers per hour. Each satellite carries an atomic clock of extraordinary precision. Your phone determines your location by measuring the tiny differences in the signals received from multiple satellites, and those measurements depend critically on the accuracy of those clocks. Now, 14,000 kilometers per hour is fast by human standards, but it is a snail's pace compared to light. The time dilation due to their orbital velocity is minuscule, roughly 7 microseconds per day, with the satellite clocks running slightly slow relative to clocks on the ground. There is also a competing effect from general relativity, Einstein's later, even more ambitious theory, which predicts that clocks in weaker gravitational fields, like those farther from the Earth, tick slightly faster. This effect adds about 45 microseconds per day in the opposite direction. The net result is that the satellite clocks gain roughly 38 microseconds per day compared to ground-based clocks. 38 microseconds. That sounds negligible. But light travels roughly 11 kilometers in 38 microseconds. If the GPS system did not correct for relativistic time dilation, your position calculations would drift by about 11 kilometers per day. Within a week, the system would be useless. Every time you use GPS to navigate to a restaurant or find your way home, you are relying on Einstein's theory of relativity. It is built into the software. It is baked into the software. Relativity is not abstract. It is in your pocket. But perhaps the most elegant and direct confirmation of time dilation comes not from technology, but from nature itself, in the form of tiny particles called muons. Muons are created when high-energy cosmic rays, protons and other particles from deep space, slam into the upper atmosphere and collide with air molecules. These collisions produce showers of secondary particles, and among them are muons, which are essentially heavier cousins of electrons. Muons are unstable. They decay. And they do so quickly. The average muon has a half-life of about 1.5 microseconds. That means if you start with 1,000 muons, after 1.5 microseconds, about half of them will have decayed. After another 1.5 microseconds, half of the remainder will have decayed, and so on. Now, these muons are created at an altitude of roughly 15 kilometers, and they travel toward the ground at very nearly the speed of light, about 99.9% of it. Even at that tremendous speed, a simple calculation shows that they should only be able to travel about 450 meters before most of them decay. They should never reach the surface. the vast majority should disintegrate high in the atmosphere, long before they get anywhere near a detector on the ground. And yet they do reach the ground, in enormous numbers. Far more muons are detected at sea level than should be possible if time passed for them at the same rate it passes for us. The explanation is time dilation. Those muons are moving at 99.9% of the speed of light, and at that velocity, the Lorentz factor is enormous. Time for the muon is dilated, stretched, so dramatically that what feels like 1.5 microseconds in the muon's own frame corresponds to tens of microseconds in our frame. The muon, from its own perspective, lives its brief life and decays right on schedule, but from our perspective it lives much longer, long enough to traverse the full 15 kilometers of atmosphere and reach our detectors. The muon is a tiny, ephemeral messenger, and the message it carries is this: Einstein was right. Time is not the same for everyone. It depends on how fast you're moving. And if you want to see this from the muon's own perspective, something equally remarkable happens. The muon does not think it lives longer. From the muon's frame of reference, its internal clock ticks at the normal rate, and it decays in 1.5 microseconds, just as expected. So how does it reach the ground? Because from the muon's perspective, the distance it must travel is shorter. The 15 kilometers of atmosphere are Lorentz contracted, squeezed, so that the muon only has to traverse a fraction of the distance. Length contraction and time dilation are two sides of the same relativistic coin. Different observers disagree about the lengths of objects and the durations of events, but they always agree on the outcome: the muon reaches the ground. The physics is consistent, even if the descriptions are not. These confirmations, GPS, muons, and countless others in particle accelerators and precision laboratories around the world, leave no room for doubt. Time dilation is real. Length contraction is real. The relativity of simultaneity is real. These are not quirks of the mathematics or artifacts of our measurement techniques. They are features of the universe. But Einstein, remarkable as he was not the only one to see the deeper structure hidden inside these revelations. In 1908, 3 years after Einstein published his special theory, a mathematician named Hermann Minkowski, who had, as it happens, been one of Einstein's professors at the Polytechnic in Zurich, gave a lecture that would add an entirely new layer of understanding to the theory. And he began that lecture with one of the most striking opening lines in the history of science. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski realized was that the mathematics of special relativity could be expressed far more elegantly if you stopped thinking of space and time as separate things and started thinking of them as components of a single unified entity, space-time. Not space and time, space-time, one word, one thing, a 4-dimensional continuum, 3 dimensions of space and 1 dimension of time, woven together into a single geometric structure. This might sound like an abstraction, a mathematical convenience with no physical content, but it is far more than that. Minkowski's space-time provides the stage on which all of physics plays out, and it reveals something about motion that is genuinely astonishing. Everything in the universe is always moving through space-time at the same speed. Always. Without exception, that speed is the speed of light. Now, before that statement triggers the entirely reasonable objection that you are currently sitting in a chair and are decidedly not moving at the speed of light, let me explain what this means. In Minkowski's framework, motion through space-time has 2 components: motion through space and motion through time. When you are sitting still, you are not moving through space at all, which means all of your motion through space-time is directed through the time dimension. You are hurtling through time at the speed of light. This is your default state. This is why time passes for you, why you age, why the clock on the wall ticks. Now, when you start moving through space, when you get up from your chair and walk across the room, some of your motion through space-time is redirected from the time dimension into the space dimensions. You are now moving through space a little and through time a little less. Your clock, compared to a perfectly stationary clock, if such a thing existed, ticks ever so slightly slower. You age ever so slightly less quickly. The faster you move through space, the more of your space-time motion is diverted from time into space, and the slower you move through time. At 90% the speed of light through space, your movement through time has slowed dramatically. At the speed of light itself, the speed at which photons travel, all of your motion through space-time is directed through space, and none is directed through time. This is why light does not experience time. It has, in a very real sense, traded all of its temporal motion for spatial motion. Think of it as a budget. You have a fixed budget of motion, precisely the speed of light, and you must spend it across the 4 dimensions of space-time. If you spend none on space, it all goes to time, and you age at the maximum rate. If you spend some on space, you have less for time, and you age more slowly. If you spend it all on space, there is nothing left for time, and you don't age at all. This is time dilation, not as a bizarre consequence of arbitrary postulates, but as a natural, almost inevitable result of the geometry of space-time. It is an exchange rate, a trade-off, a cosmic budget written into the structure of reality. And the exchange rate is governed by the speed of light, which reveals itself not merely as the speed at which light happens to travel, but as something far more fundamental, the speed at which causality itself propagates. The speed of light is the universe's speed limit, not because nothing can be accelerated past it, though that's true, but because it defines the relationship between space and time. It is the conversion factor between meters and seconds, between distance and duration, between here and now. It is the thread that stitches space and time together into the seamless fabric of space-time. This is why the speed of light appears in equations that, at first glance, seem to have nothing to do with light. Einstein's most famous equation, E equals mc squared, relates energy to mass, with the speed of light squared as the conversion factor. Light itself is almost incidental to this equation. What matters is the constant, the fundamental ratio between space and time that the speed of light embodies. And now we can return to the question that has been lurking beneath this entire discussion. What happens in the final seconds before impact? Not the impact of a car crash or a falling object, though relativity governs those too in ways too small to notice. I mean the conceptual impact, the moment when these ideas truly land, when you realize what they mean for you, for your experience, for your understanding of the reality you inhabit every single day. Because here is what the physics says: you are not standing still. You are never standing still. You are moving through space-time at the speed of light, right now as you listen to these words. Time is not flowing past you like a river. You are moving through it at the fastest speed the universe allows. And every step you take, every car you ride in, every plane you board, is a tiny, imperceptible reallocation of your cosmic motion budget from time into space. You are, in the most literal physical sense, trading time for space every time you move. The people around you, if they are moving differently than you, are experiencing time at a different rate. The differences are immeasurably small at everyday speeds. Yes, billionths of a second, but they are there. They are real. They are not a metaphor. Your watch and the watch of the person walking past you on the street are not keeping the same time. They cannot. The universe will not allow it. And the deeper you follow this thread, the stranger it gets. If simultaneity is relative, then the rigid shared now that you imagine stretching across the universe, the notion that there is a single present moment in which the entire cosmos exists, is a fiction. A useful one, certainly. An intuitive one, without question, but a fiction nonetheless. The universe is not a collection of objects existing in a shared present. It is a 4-dimensional block of space-time, and where you slice it into now depends entirely on how you are moving. This is not to say that your experience of the present is meaningless. Your experience of time flowing, of one moment giving way to the next, of anticipation and memory and the sensation of duration, all of this is real in the sense that it is your experience, and experience is the most immediate reality any of us will ever know. But the structure that underlies that experience is not what it seems. Beneath the steady ticking of your clock, beneath the comfortable flow of your days, the architecture of reality is far more strange, far more flexible, and far more beautiful than your senses will ever show you. Einstein once wrote, in a letter to the family of his lifelong friend Michel Besso, who had just died, "Now he has departed from this strange world a little ahead of me. That means nothing." People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. He wrote those words with the calm assurance of a man who had spent decades staring into the deep geometry of space-time. And he died just weeks later, having perhaps found some measure of comfort in the very theory he had created. Whether Einstein was right to find comfort there, whether the block universe of Minkowski space-time truly means that past, present, and future all exist with equal reality, is a question that physicists and philosophers still debate. It is, perhaps, the deepest question that relativity asks. It is also, perhaps, a question without a final answer, at least not one that physics alone can provide. But what physics can tell us, with extraordinary precision and confidence, is this: the universe is not what it appears to be. Time is not what it appears to be. Motion, simultaneity, duration, even the length of a ruler, all of these depend on the observer. All of them shift and flex and breathe with the dynamics of relative motion. And governing it all, sitting at the center of the theory like a heartbeat, is the speed of light, constant, absolute, unyielding, the one fixed point in a sea of relativity. The next time you look at a clock and watch the second-hand tick, remember this: that tick is not a universal truth. It is your truth. It is the tick of your clock, in your frame of reference, reflecting your particular path through the geometry of space-time. Someone moving past you would see it tick differently. A muon in the upper atmosphere would see it tick differently. A photon would not see it tick at all, and yet the universe holds together. The physics remains consistent. The laws are the same for everyone, even if the measurements are not. That is the miracle of relativity. Not that it shows us a universe where everything is uncertain and subjective, but that it shows us a universe where something deeper than any single measurement is absolute, the structure itself, the geometry, the relationships between space and time that persist even as space and time individually bend and stretch to accommodate different observers. This is what Einstein found, sitting in a patent office in Bern, thinking about what it would be like to ride alongside a beam of light. He found that the universe is stranger than we imagined, but more coherent than we had any right to hope. He found that the speed of light is not just a number but a key, and that it unlocks a door behind which the nature of time, space, and reality reveals itself to be at once more alien and more elegant than anything the human mind had previously conceived. And now, in the final seconds before these ideas fully land, before the implications settle into your understanding and begin to reshape the way you see the world, consider this: you have been moving through time at the speed of light for your entire life. Every moment you have ever experienced, every memory you carry, every heartbeat and breath and blink of your eyes has been a journey through the time dimension of a four-dimensional space-time continuum. You didn't need a spaceship. You didn't need a particle accelerator. You were always traveling at the maximum speed the universe permits. The only question has ever been, how much of that speed is carrying you through time and how much through space? The clock on your wall ticks again. 1 second. Ordinary, familiar. But now, perhaps, a little less simple, a little less innocent. And beneath its surface, humming with quiet, relentless certainty, the geometry of space-time carries you forward, through time, through space, through the elegant, astonishing, endlessly strange architecture of everything that is.